Okay, well, thanks a lot to the organizer for inviting me to speak and for putting together this very nice conference that I'm looking forward to. So what I'm going to talk about is a joint work with, as you can see, with Alex Perry, Laura Pertusi, and Xiaolei Zhao. And so let me jump right into the definition and motivation. So let me start by reminding you what I mean by generalized Kummer varieties, which from here on out will be abbreviated GKV. And the first six are, so these are all Hyperkaehler varieties. Which mean that H0 of omega 2m is generated by an nowhere to generate two form. And I want them to be simply connected and polarized. Today everything will be algebra. And the first example of a generalized Kummer variety is if you take, so for both examples, you take A and abelian circles. And you take n, let's say, greater or equal than 2. And then you take the Hilbert scheme of n plus 1 point, which of course has a map to some n plus 1a. And then by addition, this has a map to a. Let me call this big map, big plus. And then the generalized Kummer variety, the original construction of the generalized Kummer variety, is the inverse image of 0, right? So I mean, obviously A is not simply connected, and you can show that this lifts these fundamental group lifts to here. So this is not a Hyperkaehler variety, but the fiber of this map is it still has a holomorphic symplectic form, and it's simply connected. And the second example that will be in some sense more crucial for this talk is really a generalization of this one. So here I take an integer algebraic cohomology class and primitive, and maybe let's also say v squared bigger than 2. And then let's say that H is a generic polarization. And I mean, if V was a rank 0 class, I would have to make some additional assumptions, but let's sweep this under the carpet. Right? So under MH of V, then is a smooth projective moduli space. If I look at here, so the projective moduli space of H stable sheaves. You can take Giesecke stability or slope stability. And again, this is not a Hyperkaehler variety because it has the determinant map to the dual abelian variety. But then it also has a dual determinant map back to A. And so, for example, one way to construct this is you take a sheaf on D of A, you take the Fourier transform to D of A hat, and then you apply the determinant there, and then using that A hat as A, you get the map to A hat into A. Right, and this is actually also the Albanese map of this model. Right, and then here the if I take the pre-image of 0, 0. This is a again, this is a Hyperkaehler variety, and it's deformation equivalent to Kn of A, where 2n is equal to 3 squared minus 2. Right? Of course, I mean, this is actually a generalization of this construction in a sense, because if you take the V to be of rank 1, right, then you get essentially the ideal sheaf, except that you can also tensor with the degree 0 line model. And but then taking the five of both determinants map, you are doing exactly the same as taking the inverse image of the summation. Okay, and there's some mismatch of dimensions going on. So we have B2 of A is 6, right? And so this means that the moduli space of polarized abelian surfaces this is 3-dimensional. Right? I mean, where did the 3 dimension come from? I mean, you look at the projectivization of H perp intersect the quadric that omega squared is equal to 0, modular some subgroup of the subgroup of O of H2 of A comma D. Right, so the orthogonal complement is 5-dimensional, projectivization makes it 4-dimensional, and restricting to the quadric gives it sometimes 3-dimensional. Right, so but in all these cases, right, maybe let's call this M here. B2 of M is equal to 7. Right, and it's really the same argument as for the Hilbert scheme of points on Euclid V, so right, from any homology class on A, you can symmetrize one and get one in sim n plus 1, but then you also have this exceptional divisor. So you have one additional class in B2 of M, and this means that this has a 4-dimensional moduli space. And so if I define a GKV to be a polarized Hyperkaehler variety that's deformation equivalent to Kn of A for some n, then the very general GKV cannot arise from a moduli space. On a polarized abelian surface. Right, simply because of this dimension. Okay, so now I want to point out a similar missing dimensions for the derived categories of abelian surfaces. Right, so I'll always write D of A for the bounded derived category of coherent sheaves on my abelian surface. And then the deformations of that one are controlled by the second Hochschild cohomology of D of A, which is like A0 of omega h TA plus H1 of TA plus H2 of OA. Right, and so this here has rank 1, 4, and 1, so altogether it has rank 6. Right, and of course, this part here corresponds to deformations of the abelian surface. So if we were to restrict to polarized deformations, then we get a 3-dimensional space. But really, altogether, we have a 6-dimensional space. And the question is whether we can make sense of this not only infinitesimally, right? So certainly, I mean, shorter, and I'm sure this goes back to others. We showed that this can be realized infinitesimally. Right? But can we realize any of these globally? And the first claim I want to make that this is too strong of a question to ask for. So instead, I claim that we should always just look at deformations that are orthogonal to a positive definite rank 2 lattice. In the algebraic homology of A. Right? Just like when we want algebraic deformations of A, we only look at deformations that are orthogonal to our given polarization. So here I claim the polarization numerically should be given by this positive definite rank 2 lattice. And let me convince you in a few minutes. Let me try. And so maybe I can say in words while I'm cleaning the blackboard, it's nice to be back in Bonn. That's actually the experience from K3 surfaces, right? So in the cases where we have a nice deformation of the derived category of a K3 surface over a 20-dimensional space, then there's always a positive definite rank 2 lattice in the numerical K group, or the cohomology that remains algebraic, right? So for both for cubic fourfolds and for Usher-like trifourfolds. Okay, so this positive definite rank 2 lattice, if we want to hope for a derived to value result, via, right, so we take the second whole-shape homology of the category inside the topological K-theory of the category tensor C. Right, and so in the style of Alex Perry, this gives you a hot structure of grade 2 that on the abelian surface is just the hot structure on the Mukai lattice. Right, and the point is that this one here has signature 4,4. Right, and so if you take the complement of something positive definite of rank 2, then you get the right signature to get a quasi-projective moduli trace. And then lambda perp has signature 2,4. Right, and so on that one, we would get a quasi-projective moduli trace for such case. And certainly, I think if you allow bigger dimensional deformation space, then even if you were to be able to construct this over some positive dimensional base, you could not hope for an algebraic moduli here. Right, and the second reason is that the deformation theory following Mukai this tells you that simple objects in E of A simple objects E in E of A with charm character inside this lambda deform. Right? And so this means you still have a rank 2 lattice of classes of objects that exist over any fiber of this deformation of this moduli space. And that to me feels like enough geometry that you have an interesting category. Certainly if you have only rank 1 left, right, then typically categories get very determined. And the third one is that, so such a positive definite rank 2 lattice gives rise to, so there are stability conditions on B of A, where if you write a central charge of objects as the pairing with a cohomology class, then you can arrange this so that the span of the real part of omega z and the imaginary part of this omega z is any positive definite 2 plane that you start with. I mean, that's one way to formulate the Bridgeland's main result for the space of stability condition on the abelian surface is really that up to it's basically that this is the set of allowed central charges. It's exactly those, right? And so this means now if you deform deforming P of A while keeping lambda algebraic should yield deformations of stability conditions of the stability condition as a numerical stability condition. We call it stability condition sigma of sigma as a numerical stability condition. So here, what I mean by numerical stability condition is that the central charge is not just pairing with a cohomology class, but actually pairing with a class in the algebraic K group. And that makes really many, many properties of stability conditions better behaved. So the whole business about left divisors works and all that thing. So this is really the setting where we hope to get deformations as a well-behaved stability. And finally, what's really kind of related to that is if you take V in this positive definite rank 2 lattice, and then you take H in the orthogonal complement, and then up to psi, this H induces a polarization of the moduli space of stable sheaves or objects of class V. And so the deformation of P of A, keeping lambda algebraic, this should lead to deformations of MH of V and the associated so let me continue this here, and the associated GKV.
Can you raise the board a little bit?
Sorry, yeah, I'll do it in a second. And right there. as a polarized variety. Right? And this is really, right, this is very closely related to point B. I mean, someone first applying B to the objects in the moduli space just tells you that the moduli space deforms, right? But then the applying B to objects orthogonal to that and applying some determinate line bundle construction, that tells you that the polarization deforms along with it. So really D is a corollary of applying B twice, or you can think of it as a corollary. Okay, any questions so far? Okay, now let me state our results. The results are basically that we can address both of these, right? So both the missing dimensions and the deformations of GKVs and the missing deformations of D of A we can address with one construct. And that's in progress. And so we always start with this positive definite rank 2 lattice. Okay, then there exists B, just an algebraic variety over C. The dimension of B equal to 4 with a finite map to the period domain of lambda curve. So maybe let me write this out. So I take the projectivization of lambda curve inside the quadric that I already mentioned, quotient by some group of isometries of the even cohomology of A comma Z.
Minor means quasi-common?
Yes, I think you're right. And a Calabi-2 category B over B. So that such that there exists B naught in B with the base change to that fiber is just the right category of my abelian surface, and the infinitesimal deformation they are really four-dimensional. So they give you a four-dimensional subspace. Of 8H2 of and then there exists a stability position on D over V. Specializing to the given one on D of A with central charge given by lambda in the sense of C and deforming the given one on D. The given one by on D of A. And then basically as a corollary of that one, right? So any stability condition over base in our sense always comes with a relative moduli space of stable object. And so the corollary is the following: let M be a connected component of the moduli space of polarized GKVs. Then it has an open subset corresponding to GKVs arising from a moduli space of stable objects in the Calabi-Yau category. Okay, any questions on the result?
When you say two Calabi-Yau, it's relatively or?
Yeah, so basically every fiber is
When you write D equal to D of A, you mean that over B there is a standard of the varieties?
No, so here I have a category over B. Right, so in a sense, it's a module over curve of B, and it's some kind of an infinity category. So I can do base shapes. And so what I mean by dB naught is take the base shapes to this point. Right, so there's no family of varieties over B. It's just this family. You should think of D as a family of Calabi-Yau categories parameterized by B. So yeah, whenever you have a map to B, then you can do base shapes.
So in the corollary, by connected components, you mean like the deformation types of,
Yeah, what would be called polarization types? Yeah, exactly. Right.
Oh, I see. Yeah.
Right. For every dimension of the moduli space, there's still different connected components depending on the degree of the polarization and then maybe finite invariance of the polarization. And for every one of those, we can construct them. We have this construction and it arises from a moduli.
I see. So for every n and every primitive polarization degree, somehow in that command.
And maybe I should say, what does from mean? But again, the moduli space is not simply connected. So it has a non-trivial Albanese map. And so what I mean is I have to take a fiber of the Albanese map to get a Hyperkaehler variety. More questions?
Is there an expectation that this category should see inside maybe some sigma-total decomposition of some other variety?
I don't know. Yeah, it's a good question, but we don't have an idea how to construct it. We will see. Yeah, I'll explain the construction so it doesn't naturally arise. There may be, I mean, obviously many people in this room know this, but I still want to point it out as a remark that this is much stronger in the case of K3 type. Like for K3 type Hyperkaehlers, basically, I mean, we only have two infinite series of polarization types. Types arising in this case as moduli spaces, namely from via cubic fourfolds or Kushner-Mukai fourfolds. Right, but the polarization types that you can get that way are really quite restricted, right? Either coming from the A2 lattice or from the A1 plus A1 lattice. Okay, and so basically the rest of the talk will be giving you a sketch of the construction. And the idea that Laura first proposed to us was to look at the following, right? So obviously Z acts on D of A via fallback under the multiplication by -1 on the abelian surface. And then the Bridgeland King-Reed tells you that if you take the equivariant category with respect to that action, right, and it's of course the same as the derived category of the quotient stack, but that's the same as the derived category of the associated Kummer K3. So here, S is the minimal resolution of A modulo plus -1, Kummer K3. And then, but on an equivariant category, you always have a residual action. Right? And so the residual action is given by the dual group, so mu2 acts on D of S. And in fact, this action, I mean, it's not a tautological trivial one. So it was described by Thorsten Beckmann and Georg Oberlich. Yeah, so their paper was actually really helpful for us. So if anyone has Thorsten's phone number, you could tell them we really still need him. And then you can look at the equivariant category with respect to this action, and this gives you back the original category. And so that's in this context a result by equilibrium. And by the way, of course I'm aware that Z mod 2 and mu2 are canonically isomorphic, but I find it helpful to distinguish them because here, by this action on D of S is really given by tensoring with the one-dimensional representations on this equivariant category. Okay, and then the idea is to deform D of S with the mu2 action. Okay, and why doesn't this work completely straightforwardly? If you deform S as such that the mu2 action on B of S deforms. Right, and I mean there is a standard method by now to check what cohomology classes have to remain algebraic. That's exactly the same as deforming as a Kummer K3. Right, and then that's just the same as deforming B of A by deforming A. So we have to find something better. Okay, so and to do something better, I first have to tell you a little bit more about this mu2 action and total control. And it turns out the right invariant here is something that we call derived Kummer lattice, which is very closely related to the classical Kummer lattice of the Kummer K3. Right, so the K, the Kummer lattice inside H2 of S, the right cohomology of 2 of S, is that's the saturation of the lattice spanned by all the EI. So there are 16 exceptional divisors, so where here EI is the exceptional for the map from S to A modulus. Right, and of course this lattice has been well studied, so its orthogonal complement is twice the H2 of A, and from that you can work out what the determinant is. Right, but it's really much more than just the integral linear combination of the EIs. It has the integral linear combination has index 2 to the 5 inside the Kummer lattice. And for us, instead, what we have to take is the it's the following. So this is the K twiddle. This is the saturation of the lattice generated by the classes of the form 0, 2 EI, minus 1 inside the H0 plus H2 plus H4 of 8. Right. And again, this is a rank 16 lattice, as is obvious. It is a, the projection H star of A to H even of A induces an embedding K twiddle inside K of index 2. Right, and so in particular, since we know a lot about K, it's easy to deduce basic facts about K twiddle. And why is this so useful? Well, in some sense, I feel like K twiddle is almost more intrinsic than K and more natural in a sense because of the following lemma. So K twiddle is the -1 eigenspace for the induced mu2 action on the algebraic commodity, on the full on the commodity. Sorry, this is here exactly. Right, so it has in my sense, even more intrinsic meaning than the classical Kummer lattice. Right, and now by this general theory of deforming autoequivalences, this is the lattice that you have to keep algebraic if you want to deform the involution that generates the mu2 action. Okay, and now
you say this is derived Kummer lattice of anything to do with sheaves on teach autoequivalent. So there's another thing you could do and essentially trying to go back to do. We're framing like that.
I don't know. I mean, but it is something global.
Yeah.
So maybe let me also stress that, explain the following. So if you take the orthogonal complement inside the cohomology of S, then that's actually equal to 2 times the even cohomology of A, D. Right, and I mean, the way to think about this is that over Q you have natural map. I mean, this is the invariant part for the mu2 action on the cohomology. And this is the invariant part of the Z2 action on the cohomology. And so over Z, these are naturally isomorphic. And so you wonder how they are related over Z. And that's the relation. Right, and now remember that we start with the positive definite rank 2 lattice over here. Right, and this means the 2 times lambda. We call this lambda S. This is inside the integral algebraic cohomology of C. Right? This correspondence preserves algebraic classes. And now the following.
So you didn't tell us how mu2 acts on the cohomology.
Sorry?
You didn't tell us how mu2 acts on the cohomology. That's the first.
I mean,
that's the description of the action.
Yeah. So I mean that. Right, this is the result, and yeah, I mean, it's just the induced action of the mu2 action on the derived category.
Right, but it doesn't respect the grading.
No. So there's a non-trivial autoequivalence that I didn't write down, but it's written down in Beckmann-Overdyk, right? And it's just the action of this involution on the cohomology.
But we know how it. We know exactly how it looks like.
Yes. Right. In this sense, I mean, right. I mean, this is the description. Okay, and so, in some sense what we did above there, we had to keep too many classes in the derived category algebraic, namely H0 and H4 and K twiddle. Right? And so here is a simple lemma. And in some sense, this is the technical key point. So if I take the lattice 2 lambda plus K twiddle, and let's take the separation. Right, so this is a positive definite rank 2 lattice. This is a negative definite rank 16 lattice. So altogether it has signature 2, 16. And so I claim that this contains a hyperbolic plane. U by corresponding definite. Okay, so I mean, you can prove this completely elementary using Square theorem, or if you know more Latin theory than I do, like my collaborators, then you know that it follows basically from the properties of the discriminant of K-twiddle by results of Nicolai. Okay, so I claim that this lemma basically tells you what to do. If this was a class, I would now ask the class for suggestions for how to continue. Right, so of course, if you see anyone working with derived categories on K3 who sees the hyperbolic lattice, they immediately look at the derived equivalence. Right, so there exists a K3 surface T and a derived equivalence phi from d of t to d of s, so that the induced map on cohomology sends h0 of t direct sum h4 of t. This gets sent isometrically to this, to this hyperbolic plane. Right, and now what does this mean? So if you look at phi star inverse of this lattice 2 times lambda plus k twiddle saturation, right? This pre-image now contains h0 plus h4, and so a hyperbolic plane, of course, always splits off, right? And so this is just h0 of t plus h4 of t plus something that's left. And what is this something that's left? Now this is a rank 16 lattice of signature 1, 15. Right. And so if we see a lattice like this, obviously we look at the moduli space of lambda t polarized K3 surfaces. Right. In other words, deformations of this K3, where all the classes in lambda t remain algebraic, and in fact we preserve a marking with this lambda t.
So this is some moduli of K3s with an involution, I guess, because this lambda t is too elementary, or
so they have an involution on the derived category, which is what I care about. Right. So the point is, right, so let IS be the involution on D of S, right, the involution generating my mu2 action, and then from that I get IT as phi inverse composed with IS composed with phi. This is an involution on D of t. Right, and now the point is now that phi star inverse of k twiddle. Right, we don't know exactly what this is, but it's certainly contained inside h0 of t plus lambda t plus h4 of t. Right? And so in other words, and now this is the -1 eigenspace for the involution IT. Right? And so any deformation of this category where these classes here remain algebraic, here the involution deforms. Right? But in particular, this is true for deformations of of T as a polarized K, as a lambda T polarized K3 surface. And so then that means IT deforms over an open subset of lambda T, right? Really by this theory of deforming autoequivalences, which is maybe Hyperkaehler, Marquis, Delary, and Arend and Thomas at least. Basis where I learned this from. Okay, and then there's a small addition that in my paper with Alex, that up to some over some entire neighborhood, the mu2 action deforms. Right, over some entire neighborhood, B over this modular space lambda T, the mu2 action deforms. Right, and so now you're left with the
sorry, you answered the question already, but I didn't get it. So you know that the action on the lattice of T actually comes, I mean, you say it comes from another equivalent, but is there also an automorphism of T?
No, it's not an.
Because there's no polarization therefore?
I mean, the -1 eigenspace is not contained in H2. I mean, okay, so I mean, I'm sure you could find examples, right? All depends on a choice of lambda, and it might be possible that you've actually no, it can never be an automorphism of T because these are classified, right? So it would have to be a symplectic automorphism of T, and then it's just an encoding kit. Right, so we have the situations we have, right, ignoring issues of the existence of universal family, we have, which we can of course resolve by doing another entire neighborhood. Originally that is given in the right way. So we have a family of lambda T polarized K3s over B, and we have a mu2 action on B of TB. That's somehow fiberwise, so it's an action over B, right? And then I just set D to be the equivariant category for that action. Right, and inside here I still have this, but if I took the B0 and B such that T B0 is my original T, right, in that case then B base change to B0, so is B mu2 base change to B0, that's just my D of T mu2. And so that's my original D of A. And then, so that gives me the special fiber that's equivalent to the original divided category. Right, and the, I should also say, right, so the, I framed this at the beginning in terms of that this B lives over the period domain of lambda perp. And I mean, there's some identification going on between lambda perp inside the H even of the abelian surface and this lambda T perp inside H2 of T. Again, this is up to rescaling by 2 and comes from this identification of the algebraic homology of A as the K2. Okay, and so that explains to you how to get this family of Calabi 2 categories that we call families of non-commutative abelian surfaces. And then I should tell you how do we construct stability conditions. And here we really use the old construction by Maprime, Roger, and Stellari. Okay, the idea is that let me first state this on T, right? So that the mu2 invariant stability condition on B of T, this yields a stability condition on the equivariant category. Right? And basically, and it's maybe fair to say that this part is more appropriate than the others, this is the part we deform, right? So we don't apply some abstract machinery, we're not trying to use some abstract machine of deforming stability conditions. Instead, we are on this family of lattice polarized K3, we construct a family of mu2 equivariant we construct a mu2 invariant family of stability conditions. On this E of TB, and then using this MMS construction, you get a family of stability conditions on the equivariant category. Right, and then maybe let me conclude by saying that the to get to GKVs, right, this construction of family of stability conditions, this always comes with relative moduli spaces of stable maps. Of stable objects. Right, and then what we have to prove is that you can do basically that is, again, that you can take the fibers of other neighborhoods. Okay, and maybe let me conclude with one more remark at the end. This is, in one aspect, our results are maybe not quite as satisfactory as we would wish them to be in an ideal world, right? So, I explained to you that this map of to period domains, right? And ideally, you would like this to be induced by the hot structure on the category in the sense of Alex Perry. But at the moment, we don't know how to show something like this, right? So basically, we don't know how to show that the K0 top of these categories, that they are just the Z2 invariant part of the K0 top of the K3s, right? So this is true on the special fiber where you have the Kummer K3 and the abelian surface, because there we know the K0 top is just the even cohomology, and there we know that this relation holds, but we cannot prove this in general, right? And so, I mean, already statement saying that K0 top would be is a local system over the base with this conjecture, this would imply something like this. And then all these, these maps to moduli spaces that appear here from the construction, they would be natural Torelli maps. Okay, let me stop. Thank you.